We fear no one, oh no, here they come. That element clan, road rescue shogun. Dropping 200, Kermantle, down like what? And rocking killer beats to the ear drum. Click your meters, tip your hats. I got ice water flowing up.
All right, tonight we're going to take a look at integrating the Capstan equation as a heuristic into your toolbox when you're doing vertical stuff. It's going to be very specific to the Capstan equation and how it relates to descent control devices for the most part tonight. At a later time, we'll get into all the other ways that you can use that Capstan to be able to estimate friction that exists in your system, including over edges or multiple edges around door frames, things like that, if you're doing hasty bailouts. So tonight we're going to kind of revisit this subject again, go into a little bit more depth, and talk about different ways that you can include this into your repertoire. So just starting off, as a quick background, we reference a bunch of Stephen Attaway's stuff in here. Unfortunately, Stephen passed away a couple of years ago, but he added a whole bunch of incredible stuff in that Albuquerque area and into the vertical world as a whole on different ways of looking at some of the more advanced physics of vertical rescue and access. So what we're looking at on this is the mechanics of friction and rope rescue. It's the one solid that exists no matter what you do. If you're doing something vertical on a rope, you will always need to understand friction and how to exploit it or manipulate it the best that you can. As a simple kind of rule of thumb, friction is always our friend when anything is being lowered, whether it's a casualty or it's ourself on rappelling. And it's what really keeps us from going 9.8 meters per second squared and cratering, versus friction's our enemy when we're trying to haul. So being able to exploit those two things once we understand a little bit more of what can make the biggest impact for us when we're doing that. And that's kind of what how we use the Capstan equation in an understanding. Quote out of one of Attaway's is, using this simple friction law leads us to conclude that frictional forces for rope depends only on three things: the tension in the rope, the coefficient of friction, and the total angle of contact, which is pretty true, kind of true within the context and specific assumptions. We're going to talk about those towards the end. This is not one of those things where you plug it in and it's guaranteed to be exactly what you need. It does give you a really good rule of thumb. It gives you the ability to understand what is the exponent in my system, what has magnitude, not unlike looking at a magnitude of, let's say, an earthquake, where from looking at the Richter scale on seismic activity, right, we go from a 5 to a 6. That's on a scale on a magnitude of 10, yet the energy is on a magnitude of 30. So when we get into exponents, that becomes the critical part of any system that you're ever going to look at, whether you're looking at how to manipulate friction or how you're looking at what kit should you wear on your harness. What is that assault loadout compared to doing an expeditionary type of loadout, or what goes into your medical assault medic bag versus medic bag that you're using on a recce or something like that. So when we look at it, knowing your system really well is going to help template really where the exponents are and where it's really that, we'll talk about this in a second, it's kind of that Pareto law of 80-20. What can I do that's a 20% input into my system but get an 80% output of it? And what we'll realize is on these two, the coefficient of friction and total angle of contact are the most critical, versus the tension on the rope, which would be how much does my load weigh? How much do I weigh slick versus in full kit, etc. Moving on, heuristics. We have the GERD type and we have the common type. So as a quick background, there's always these arguments through these really smart people on the use of heuristics. And when we get into Kahneman and Tversky, for people that have read, Thinking Fast and Thinking Slow, and you're going to see a little bit of a negative context to how they talk about heuristics, versus how GERD does it at the Planck Institute is very, very different. And where that difference comes from is GERD hits it from, you have to make very quick decisions and you do not have time to do all the research and pull out a scientific calculator and do all these kind of things. So creating deliberate design heuristics is what GERD talks about. When we look at the arguments against heuristics, those are typical heuristics kind of correlating to biases that we have in our brains a little bit on certain things. That is not what we're talking about. We're talking about knowing your system well enough that you are able to create rules of thumb that you're able to go through. There's a great quote there at the bottom there from one of Gerd's paper talking about heuristics are frugal. That is a ignore part of the information, unlike statistical optimization procedures, which is what typically you find Tversky and Kahneman talking about, is the optimization, which means if I don't have that information, I'm going to research and dig in, get that information, and then make a decision. Gerd hits it from, you have no time to do that. You're having to make decisions very quick when you don't even really know everything that's going on, but it needs to get in that ballpark. So continue on that quote. Heuristics do not try to optimize or find the best solution. Rather, they try to satisfy, which is a combination of words that a guy named Hubert Simon came up with years ago and is also won the Nobel. But calculating the maximum of function is a form of optimizing. Choosing the first option that exceeds an aspiration level is a form of satisficing. So we are never going to be so exact that we can sit there and put equations to anything we do dynamically in the vertical realm, especially when we start thinking about having a emergency egress called over the radio to where we've got to grab whatever anchor we can and get ours and everybody else on our team's butt out of a 4 or 5 story window and get to the ground. It's not the time where we're going to be really evaluating every possible opportunity that we have, looking at 3 or 4 different anchors and talking to ourselves, what do you think about that one? What about this one? It's going to be, you have very limited time before potentially the building blows up or you're overwhelmed with fire or whatever that egress was called. So this is the heuristics where they're very deliberate and very designed. The MUNTER HITCH is what we're going to take a look at. It's used quite a bit with the groups that we typically work with, although we do have certain descent devices, whether it's a totem or an aid or an auto-locking device. MUNTER HITCH is kind of that go-to, and it allows you to keep going. By understanding the components of it, it allows you to move fast and light, not having to switch out descent devices or friction-mediated devices and gree-grees and things like that. So what we'll do is we'll take a look at the MUNTER HITCH. This is looking only at the holding power, meaning the static coefficient of friction. So if I'm on a MUNTER HITCH, how much force does it take for me and my brake hand to hold myself still, not moving at all, just static? I just roll out the window and now I'm on my hand. And then how much force is it going to take to be able to hold myself without moving? So when we get into the equipment that we used with these pictures, and how we went about this, we used a 7.8 millimeter aramid nylon rope. So really the main thing that's concerning coefficient of friction is the aramid and what that coefficient of friction is with an aluminum 7075 carabiner with a large rope bearing radius. We utilized to kind of check our math and see how in the ballpark we were. We used a hanging crane weight scale that measures up to 1,100 pounds and some Rock Exotica enforcers to kind of see how in the ballpark we were. With this, we tell you this information because you'll see that one of the downsides that people don't understand really with the Capstan or the belt friction equation is if I change my rope, not even diameter, just the manufacturer or the materials that it's manufactured out of, it will change my response, my answer. It'll change what those angles are if it's a stiff rope versus a very soft rope. There's so many different factors. It doesn't account for the nonlinear behavior of ropes or the bending rigidity, but it gets us in that ballpark and it allows us to understand how we can work things out dynamically when we don't have time to think about everything and we don't have a lot of equipment. So when we're looking at this, what we're doing is I just took a PNG of a protractor 360 to be able to kind of estimate the values and the angles that we have inside this. And we have this available, so you can just take this on your computer, take pictures of the brake position of any descent device you have, whether it's an 8, whether it's a bar rack, whatever you have, using a scarab, whatever, and you'll be able to see and get in that ballpark of how much friction, how much holding power you have with all those. And so you can just download this on Element Rescue. So when we're looking at this, this is the first angle. There's 3 angles that we're going to look at in a MUNTER hitch, and we're going to go through all 3 of them. I do want to preface this, although we have it in a later slide. At no point am I saying that you should roll around with a protractor, a scientific calculator, understanding what Euler's or Euler's constant, depending if you're speaking German or not, constant is, memorizing all this stuff and walking around with a calculator watch or some goofy crap like that. That's not at all. What we're showing you is the science behind the heuristic that we're going to be talking about, so you can make quick decisions, only having to keep a couple factors in mind to be able to make huge impacts onto your system, usually without adding hardly any gear to your system whatsoever. So on the first one we were looking at, and I'll kind of go back and forth and expand these out, this is the first angle we're looking at. For context, the line on the right is your brake cam. The line on the left is what's coming from the anchor. So when we go in here, we take that brake strand, and in a full brake, which is parallel, obviously I can go a little bit further, as we do when we're doing vertical stuff. I can overextend that a little bit, as if I was going to go into a monster MUNTER tie-off or something like this. We're keeping it just parallel with these lines. And so with that, we have 0 here, and that's basically estimating where the rope is in contact and coming up to the center of our point and our carabiner, and then going off to where we lose contact of the rope with our brake strand. So we're estimating that right at about 275. So going back here, you can kind of see kind of right in between there, 270, 280. So we estimated that at right at about 275. So that's our first angle. We can mark that down. Now we look at the second angle. That second angle is the point where this is the line here on your right-hand side this time that's coming from the anchor, running underneath the U of the rope that it forms, around that carabiner, and then bending into what does come into contact with the rope. So that is going to be our third angle that we're looking at, where it's rope on rope. All we're looking at is the contact that it has with the aluminum 7075 carabiner in that. And we estimate this one at 330. So to kind of look in there, you'll see where we're at. There's 0. It's where it kind of comes in contact. 330 is right up here. So we're estimating it, it's a little ballparkish. We're not pulling out calipers and doing everything crazy on this one. So we estimate that one at about 330. Now we're looking at our final angle here, which is looking at it from underneath. The line that's coming straight towards you is that which comes from the anchor and does that large. So all we're looking at is the friction that's created with this rope running through and between the aluminum carabiner, looking at the angle of contact with the rope that comes around the bottom side of this MUNTER hitch here. So same way, we estimate this one. We plot here at about 130 degrees. So all we're looking at is just this contact portion right there. So there's our 0 coming in, where it just starts to hit rope on rope contact. We follow that right around here, and we're coming out right at around 130. So from there, this is where all the excitement starts. So when we put it all together, now that we have our 3 numbers, 275 degrees, 330, and 130, we add them together. So we add them together and we get roughly 735 degrees. What we got to be able to do is turn around and convert that into radians pi, or pi radians. And all we have to do is take that 735 and we divide it by 180. It's 180 degrees. So divide that by 180, and this is what we get is 4.0833 pi radians. When we plug this number into our actual equation down here, we're going to have to take pi out. And to do that, we're just going to times that by, and we'll estimate that, we'll round that down to just 3.14. So right there is the first exponent that we have. The next one is estimating the coefficient of friction. There's a lot of cheating that goes onto this, and it always is really an estimate. So we know that for the most part, when we look at aramids of semi-new ropes, we're looking at about a 0.25 coefficient of friction when we put those together. So remember, a coefficient of friction is how easily does a material slide across another material. So for context, 0.25 is a pretty low coefficient of friction. But let's say we took that same aramid rope and we ran it across a brick or poured concrete. That's going to be a higher coefficient of friction. when we look at it, a lot of times we have a higher coefficient of friction when we deal with steel and some of the anomalies that exist in there. So for this, we were able to take a lot of other studies and estimate that to be about 0.25. But also remember, depending on the material your rope is made out of, that coefficient of friction can either get higher or lower if it's wet, or the rope is worn more, or you're in super hot conditions, or there's a lot of grit in it. Those things all change your coefficient of friction. And it may not seem that big of a deal, but you're going to see, because the coefficient of friction and the angles are both exponents to what's called Euler's constant, they actually make an enormous difference. So with that, we estimate that to be about 0.25 for a new 7.5 millimeter Aramid rope and an aluminum carabiner. So we take those numbers and we plug them into the Capstan or belt friction equation. So taking a look at that real quick. Basically, this is the force that you'll have to input to hold yourself still. This basically comes down to the weight, and then here is your Euler's constant, which is this E, and this is the mu sign, which is for coefficient of friction, and this is your angles. So when we put that into, this is Euler's constant, so just like pi is 3.14, blah, 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 Euler's is the same thing. It's 2.718, blah, blah, blah. It goes on for a while, so it's a constant. So this will always stay what it is. So I'm going to bring a calculator over. Most calculators have a little bit of a capability of doing Euler's on it, or some sort of scientific type of capability in it. So when we look at this, this is from Calc Made Easy. It's free. You can get a free one on any of the app stores, but the ones that come on your Macintosh or whatever system you're using usually has it. And what we're worried about is this sign right here, which is just the E as in Euler's constant, and the X. The X is what we're going to be plugging in for the exponent. So I'm going to try and get this out of the way a little bit here. So when we look at this, we take the original number that we got, which is 4.0833, and we times that by 3.14. So this is the number with the angles. This is when we divided it out to pi radians to get that. Now, by doing this, we're taking the pi out of it. Then the 0.25 is obviously our coefficient of friction. So after we take the pi out, we get 12.821. And those two things are multiplied together to become the exponent for Euler's constant. So just to show you on a calculator real quick how to do this, and then we can skip over this in the future, is I can take those two numbers, 0.25, multiply that by 12.821, and I will get, I erased it. Don't do that. Don't do that. I'm going to get 3.205, but we'll walk through this again, even though I absolutely sucked at my calculator operations right there. All right. So 3.20525. So we round that last part off and we just go with 3.205. That is our exponent. And now we just have to put that into the Euler's constant. So all we have to do is come up here to where that E with the X exponent on there and hit it. And that's where we get the 24.661664, blah, 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 blah. So roughly we get a 24-to-1 holding power in there, which means that if I'm weighing in at 240 pounds or my load is 240 pounds, the casualty that I'm lowering, minus any other issues with friction on over edges or windowsills or anything, that if I'm working straight, let's say like in an elevator shaft, so I have no other friction except that which I'm gaining into my MUNTER hitch, I will have to put about 10 pounds of force on my brake strand to hold my 240 pounds static. So that's kind of the rough estimation of what we're doing here. So let's take a look and dig into this just a little bit more. So the variables that exist in here are quite a few. So a coefficient of friction is a bit difficult to predict, but makes an exponential difference. So what I would end up saying is we can kind of back end to these numbers if you're trying to figure that out at work or anything like that, by taking just even just a rough luggage scale and things like that to see, and put a rope grab on, see how much force it is with your weight, weigh yourself accurately on that same scale, and you'll start to be able to back in what that rough estimation is of your coefficient of friction. But I can tell you that 0.25 is a great spot to start off with. So those can change based on condition of rope, material, and the properties of those materials. Your hardware can change it. Are you using steel? Are you using aluminum? Are you improvising this over doing a lower with just a 1 wrap or a 2 wrap around a balcony handle, or in a stairwell doing a stairwell's corkscrew? So test your equations out, and it's basically a balance of inequalities, and one way or another you'll be able to kind of get a rough estimation of the gear that you carry, and then from there it's extremely easy. So these are a couple other examples I just want to show you, and we're going to really look into this top one to prove the point for systems as a whole, not just for the sensitive devices. So you can see with Attaway, he's got a bunch of different examples in some of his papers using a bar rack and showing how these angles within it make a very big difference. So if you look at those loose angles, and he's got one of his bars released on here, he's getting about a 4-to-1 factor compared to what we were getting on that MUNTER hitch of 24-to-1. Now, by adding that extra one in and keeping the angles somewhat loose, he's able to raise that up to basically a 12-to-1 holding power. But by cranking that down, as we do when we're going into those brake positions on a bar rack, if you're doing a huge descent of seal in a cave or something like this, this is where it bumps up from 12 into 31. And when you think about it, the coefficient of friction never changed on these two. It did a little bit on this one because we added an extra bar. All that changed was an angle. So just by changing those angles, it has an enormous impact onto what we're seeing as far as the output. We understand this is a nonlinear system. People try and use linear type of equations and math to show things, and it always works out really good in a textbook and on a whiteboard when we're talking about anything from high tension lines, high lines, things like that. When we put it into reality, we don't get those numbers. When we put the dynamometers on, we put the enforcers on, you don't get those numbers. And the reason is they're using very linear style math. Newtonian type things is linear in nature compared to nonlinear stuff, which means everything acts together. And it's very hard to predict until you actually try it out. So this is nonlinear nature. And for something to be nonlinear nature, one of the first principles to separate it from something linear is that your input is not proportional to your output. It's not additive, it's multiplicative, it's an exponent. And that's true throughout almost all of your nonlinear and linear comparisons. It works on this kind of 80-20 Pareto principle that doesn't fit into a Gaussian curve. So that's really what we need to focus on when we're looking at systems as a whole. We're looking at loadouts, we're looking at those things, is what 20% effort can I put in to get an 80% result? And anytime you have an exponent, which means anytime you're working a nonlinear system, which is everything you do in life unless you work in a laboratory. If you're, firefighter, medic, DoD, special operations, you name it, those are all nonlinear environments. You will have an exponent or a period of magnitude in all of those organically. So finding that exponent becomes very critical, and you'll see what happens. So if we're going to look at this one real quick, because we're going to use it for an example on a couple other things to really drill this home, is on this, it's telling me that I have a 2,000 pound load, and it will only take 7 pounds of force, input force on my brake to keep that hanging there static. So I can hold that static hanging in the air with 7 pounds of force, given I put 3 wraps, 360-degree turns around this pipe, pole, whatever they're using here. And that pole has a coefficient of friction of 0.3. So we're looking at probably something bolted in really strong, and it's probably steel in nature. And I'm getting a mu, or a coefficient of friction, of 0.3. So when we work that out, we do exactly what we did before. So we add the 360, we have 360-degree angles, which comes out to being roughly 1080. We take that 1080 and we divide it by 180, and we get 6 degrees radian pi. Now what we have to do is go through and plug those numbers in. So here's obviously the Euler's constant, which is already provided for us in our calculator, so we don't have to worry about that, but just showing you the longhand of this. We know that the coefficient of friction is 0.3, so that's plugged in there as an exponent. The other exponent has got to get pi taken out, so we go 6 times 3.14. And then we multiply those together and we get 5.652. And what we get is this huge number of 284.8606, etc. So what that gives us now is an ability, because we know the weight of our load. So all we do is take that 2,000 pounds, divide it by the number we have here at 284.8606, and we get roughly 7.02 pounds. So that is where we get the 7 pounds to be able to hold 2,000 pounds. If we do 3 full turns, 3 360-degree turns around an object that has a coefficient of friction of 3. So looking at this, where this comes in now is we understand a smaller, we don't understand it yet to the magnitude we will here in a second, is if I can focus on the exponent, that is where my focus and improvisation needs to come from, is the exponent, because small changes have a huge alteration in my system. But it's not always natural. You have to know your system really well to find out where those exponents are. So this is kind of a given in here, so we can play around with it to show the importance of it. So if I would say, listen, let's mess with this equation a little bit. Let's keep everything the same. Let's keep the coefficient of friction at 0.3. Let's keep the turns around that pipe the same. So we'll do 360-degree turns. But let's change the weight. So let's increase this weight. And let's take a quarter of what its weight is right now. So a quarter of 2,000 is right, 1/4 of it is 500 pounds. Let's add another 500 pounds to it. So from a rope rescue access type of system, that's equivalent, if not more than, adding 2 more people onto a rope. So that's significant. So if at any given time you're like, hey, you're controlling that fine with your MUNTER hitch or with whatever you're using, I'm going to add another 500 pounds to that. That tends to create some anxiety into the rest. You're like, oh shit, man, I've got to re-rig the system. I've got to add something with a ton more friction if I'm going to be able to hold that friction to be able to lower, let's say, something that heavy or that big of a package that I'm lowering off that. I need to re-rig this thing, potentially add a bunch of shit into it, go to a bigger device. Maybe I need to get into like an ID or something like that. When in reality, you probably don't. It's not as big of a issue as it is, because the weight that you're dealing with is the tensional force, and that tensional force is not an exponent at all. The angles and your coefficient of friction are. So just to do a comparison to kind of prove a point is, let's compare, what if I would add 500 pounds to this load? How much more weight would you have to be holding to keep it static? So, if you're thinking about re-rigging, or, oh my God, I've got a MUNTER that I'm able to, hold, or whatever, depending on what your weight is. I've got a MUNTER now because I'm adding this much more weight. I may have to switch to like a monster MUNTER or do all these other crazy stuff and add goofy loops all over the place and crap like that. And in reality, you probably will not have to. So we're going to compare a 500 pound increase in weight compared to, let's keep weight at 2,000. And example number 2, we'll keep the weight at 2,000. We'll keep the wraps still at 3 360s, but let's just change the coefficient of friction by 0.1. So we'll decrease it from 0.3 to 0.2, and then we'll see where the biggest impact comes from. So on that, right, we can find that exponent or magnitude in our nonlinear system. We'll then have fidelity on what can be leveraged for the largest impact with the least effort. This is where our focus should be during dynamic operations. So the original example we have right here, which was the 7 pounds to lower 2,000. Now on example number 2, we're going to add 500 pounds to our load. So we're going to keep everything the same, except at the end, we're going to divide it by 2,500 pounds instead of 2,000 pounds to see, by adding 500 pounds more to the load weight that we're going to be trying to handle, and keeping everything else the same, and we plug these numbers in, we see that really it didn't make crap for a difference. We actually only increased the amount of force that we have to input into our brake line by 1.75 pounds. So we went from holding 2,000 pounds, requiring 7 pounds of force, to holding 2,500 pounds, only requiring 8.7 pounds of force. And the reason for that is we didn't change the exponent. All we did was change a linear portion of this, which ends up being very nominal. It's very normative in nature, very simple. Although when our brains hear it, we think that's the biggest thing. The weight of the load is the biggest thing, right? That dictates how we're rigging. And in reality, it's not. We can make very small changes to our rigging to accommodate that all day long. So adding 500 pounds to it only increased the amount of force that we'd have to input to break it by 1.7 pounds of force, which I think everybody can deal with. On our next example, we are going to go back to the 2,000 pounds of the original example and not changing any angles. All we're going to do is change the coefficient of friction from 0.3 to 0.2. So we're going to only alter that down by 0.1. So when we look at this, here's our one that we did on the page before with the 500 pounds that we got 1.7 pounds difference. Now all we're going to do is keep those same numbers the same. So it's still 360 degrees. All we're going to do now is change that coefficient of friction from 0.3 to 0.2, fill all those in, and that actually bumps it up. So whereas before we only needed 7 pounds to hold 2,000 pounds, now just changing the smoothness or the coefficient of friction of this pipe, we jumped all the way up to 46.2 pounds of force that we're going to need, which is statistically significant. That's quite a bit more that we're going to have to keep in consideration. So now instead of having a 1.7 pound difference, we actually have a 39.17 pound difference in what it is. And the reason that is so drastic is by manipulating the exponent, that's where the magic happens. So in the end, we've had people with 6 millimeter X-Tech rope, and we've had them put it onto a large 8 plate that's made to hold, 10 millimeter rope, 11 millimeter rope. And when you take that 6 mil and you look at that, people will freak out. They're like, I will not even be able to break on this. This means nothing whatsoever. I'm going to crater into the bottom. And so you'll see a lot of different things where they're adding MUNTER hitches onto something else that then feeds into this 8 plate, and maybe you'll see them double loop around there. They'll switch the 8 plate, which is normally clicked into a carabiner, flip it upside down. So now the big part of the 8 plate clicks into the carabiner on your harness, and they rig it through the small little hole over there. You'll see some crazy stuff. When in reality, for the most part, all you'll have to do is clip a carabiner into your leg loop of your harness. And as you normally brake right on an 8 plate, we're braking thumb up your butt, right? So it's braking behind you, is flip that through the carabiner. It's called a lap dance. Flip that through the carabiner and now brake up. So what I did is I added an exponent, which is I added a coefficient of friction into that system, which is an aluminum carabiner. And on top of that, I also added another 180 degree angle. And what you're going to find is it can take that 6 mil, and you're probably going to be able to control yourself very, very easily, way easier. So we'll rig that on somebody, and they still believe and wholeheartedly that they're going to crater. That there's no way that just flipping this through this carabiner and putting it into a 180 degree is going to make a change that's going to keep me from falling extremely quick, completely out of control. And once they get over that edge, they're amazed that it seems like it's a freaking unicorn magic trick. But in reality, it's just because we're able to identify what is exponential in that system. So small changes have big outcomes on them. So winding this thing up, back to the MUNTER. What if you need more friction? People usually jump to the monster MUNTER, when in reality, that's probably not needed unless you're looking at a load that's in excess of 600, 650 pounds without any other edges giving you help, right? So if I had an edge, let's say of granite, or if I'm in the mountains doing this, that edge is going to help me out tremendously. It's going to take weight off my anchor. It's going to take weight off the amount that I'm going to have to control them with, because that edge takes a bunch of that weight. But if I'm in an elevator shaft and I have no other edges and nothing else adding to the coefficient of friction of my system, adding friction into my system, then I may have to think a little bit different about it. But for the most part, if we go from a single load, let's say, to a 2-person load, and these are people in full kit, loaded out, we typically only need to add an extra carabiner. So this is kind of a bottom and front and bottom size effect of adding a second carabiner. So by adding a second carabiner, I'm changing and altering the angles, and I'm adding a coefficient of friction in there. Black Diamond did a great thing years ago with people that were trying to rig their ATCs with 2 carabiners, and they were thinking that by adding that, I'm decreasing the harshness of the angle. So it's going to make it easier for me to belay out rope. If I've got a guy that's doing lead climbing or trad climbing, I can belay him easier by filling that out. Or if I'm bringing a guy up, it'll make it easier. And the opposite is true. It provides you with much more control, much more friction. So try and play around with that. If at any given time you're rocking a MUNTER, whether it's a 7.5, 8 mil, 6 mil, throw a second carabiner on there and watch how much more friction that you have. So if you're able to be in control running that thing as it is, put a second carabiner on, and as soon as you get out, you're going to find that you're going to actually have to probably, even just hanging right out of a window doing a bailout, you're going to have to feed that rope through to even get moving quick whatsoever, or completely open up your break-in. If the increase in friction is not huge, like really significant, just go for, you can do a double carabiner, and that would probably be the way to go. You can mess around with a 1.5, but there's really no reason to alter the knot that you're using, or use a knot that you don't use quite a bit. Just add a second carabiner into your system, into the same hole, obviously, that your MUNTER runs through, and you'll probably be squared away. So what the hell does all this mean, right? Like we said before, we don't carry a protractor or scientific calculator operationally. Now that you understand friction at a micro level as it's concerned, a little bit maybe with edges, but really as far as descent devices go, you can now make better decisions with a lot less equipment without wasting time re-rigging things. And even if you're going over an unknown height because you can't see the ground, you're in a canyon, or you have an overhang and you can't see where that is, it gives you the opportunity to say, okay, I'm just going to put a lap dance in. I'm going to run my brake through this. And if at any given time I have a hard time braking this, I know that once I turn that brake from behind me up into more of a vertico style where it's up in front of my face, like a MUNTER hitch normally brakes, I'm going to have more than enough friction. So now you can put in like requisite diversity or redundancy that's smart into your systems, to where even if you do run into issues with it being a longer rappel than you initially thought, you're going to be able to make up for that and add friction on the fly by making small adjustments to your system. Same thing as if you're lowering a casualty and they're doing a pickoff without having to be like, oh God, I'm good with the pickoff on this. But once they put another person on double that weight, I don't know if I'm going to be able to control it. Just add a change of direction from your anchor point and brake in the other direction. You probably will be fine, but definitely go out and play around with this. Use it to shut people up. Use it not to get more complex or complicated in the way that you rig. Use it to not have to carry more crap with you that you don't need. And use it not to hurt yourself or your casualty. The take-home points is coefficient of friction and angles are an exponent. Always build a way to increase or reduce friction in your system. When could I use more friction? When do I need less, right? Hulls versus lowers and rappels. Think about edge rollers for a second. So, when we look at edge rollers, because now that we know the coefficient of friction is an exponent, you could probably get away with not carrying huge edge rollers all the time. And on top of that, remember, if I'm lowering somebody and I don't have an entire technical rescue team with me with everybody's hands on this thing, it's just me operating to lower this guy, just get the edge roller out. Don't use an edge roller. Use even one of the plastic thing, or use something that even has friction on it if you can. Throw a bag or whatever, a jacket or anything underneath there over that edge. At least that will protect your rope if that's your main concern, and you don't have a real abrasion resistant rope, or you're not using an air mitt. Throw something on there that's going to protect your rope, but throw something on there that's not a pulley, or else you're just working against yourself on a lower. At the same time, don't get crazy that I have to have these high efficiency bearings on the edges to be able to run my hull system up, to be able to bring that mechanical advantage, that theoretical, closer to the real actual mechanical advantage, because you can get away with just changing a coefficient of friction and having an exponential return in there. So you may not have to go as heavy with edge rollers and crap like that, and we never use them, and still have the ability for one person to do a raise on a 3-to-1 or a 5-to-1 simple or complex, and be able to get them up with a 90-degree edge just by placing some stuff. And we'll do a PowerPoint showing you some of the equipment that we use to do that. You can get away very, very small, very cost efficient, and not bogging you down having to carry extra crap. And like we said before, the lap dance is an easy one to remember. So we're getting ready to do a bunch of series of these video casts. We're going to redo the old ones that we had as far as mechanical advantages, counting tensions, and then counting efficiencies, getting into certain loadouts and how to think about doing loadouts in a different way of what redundancy is, and more into a requisite diversity to where you have much more options with a very small input. So if you have any ideas on things that you'd like to see, definitely hit us up at info@Element Rescue. And if you have any questions, hit us as well. So thanks.
We fear no one, oh no, here they come. That Element Clan, Road Rescue Shogun. Dropping 200, Kern Mantle, down like what? And rocking killer beats to the eardrum. Click your meters, tip your hats. I got ice, water flowing up both my calves. Sand flowing down.